Welcome, curious minds, to the deep dive. Today we're embarking on quite an intellectual journey. It's into a question so fundamental, so deeply woven into our daily lives, that you might not even realize you've been grappling with it your entire life.
Hmm.
Think about it for a moment. Counting your fingers, maybe measuring ingredients for a recipe, calculating a tip.
Sure, yeah, everyday things.
Exactly. Or just, understanding the time on a clock. These acts feel so universal, so incredibly natural.
Like they're just part of the world.
Right. Almost as if they're simply inscribed in the very fabric of the world itself. Numbers and shapes and patterns are just, well, they're just there.
Yeah.
But beneath that comforting familiarity, there lurks this profound philosophical mystery. If these mathematical concepts and operations feel so inherent to reality, what is mathematics, really?
That's the big one.
Is it something we discover, like, I don't know, an ancient ruin or a new star, patiently waiting for us to uncover its secrets? Or is it something we create, a brilliant invention of the human mind, like composing a symphony or designing a machine?
And that right there, that's the core dilemma, isn't it? It's what has spurred philosophical inquiry for millennia. It shapes how we understand not just mathematics, but reality itself.
Okay.
Are numbers in geometric forms? Are they eternal, perfect truths existing independently, beyond space and time, just waiting for us?
Like a hidden landscape.
Exactly. Imagine a realm where the ideal circle or the perfect number 3 exists, immutable and true, regardless of whether any mind ever thinks about it.
Right.
Or are they, as others argue, fictions of the human mind? Incredibly useful tools, yes, that we've invented to bring order to a messy world, but ultimately artificial constructs.
Useful fictions.
Useful fictions. Or perhaps, and this is where it gets really intriguing, is it something else entirely, like a generative principle maybe? A kind of foundational hum underlying both the mind and the cosmos?
Like a code.
Sort of, yeah. A primal code that gives rise to reality itself. A reality that's mathematical at its very core.
Wow. Okay, so that's our mission for this deep dive then. To give you a shortcut, maybe a concise yet thorough understanding of the history of mathematical ontology.
Ontology, yeah. The study of being.
Right. And mathematical ontology, just to put it simply, is that deep, persistent search for the being of mathematics. What it fundamentally is, where it comes from, how it relates to existence. We're going to trace how some of the greatest thinkers across cultures and epochs have wrestled with this. Does mathematics merely describe reality?
Like a map describes a territory.
Exactly. Or does it actively construct it through our minds?
Shaping our perception of it.
Or, and this is the big one, does it actually constitute reality? Meaning the universe is mathematical in its very essence.
Those are really different possibilities.
They really are. Consider those distinctions. Does mathematics simply give us a precise, elegant language to describe the universe, like a meticulous reporter documenting events? That's one view. Or do we, through our mathematical thought, somehow actively construct reality, giving it form and order, imposing our mental frameworks upon it?
Like Kant might argue later.
Right. And the most mind-bending idea, one that echoes through many philosophies we'll explore, does mathematics actually constitute reality itself? Meaning the universe is mathematical at its core, not just something we can describe mathematically.
That's a profound claim.
It really is, and this isn't just a linguistic difference, it's a fundamental difference in how we understand existence.
Exactly. And these aren't just abstract musings, confined to dusty philosophy books.
Yeah.
The answers these historical figures offered, the ways they grappled with the being of mathematics, they profoundly influenced and laid foundational stones for all of science, for philosophy as a discipline, and even for our metaphysics, our basic understanding of existence. And along the way, well, we'll uncover some truly surprising facts, I think. We'll delve into specific examples that bring these ideas to life, and hopefully spark more than a few aha moments about something as fundamental, yet still enigmatic as numbers.
So we'll trace this rich, winding history, explore how each era built upon, reacted to, or, challenged previous ideas, ultimately preparing the ground for what our source material presents as a new synthesis. An intriguing vision of mathematics as emergent coherence, generated by what it calls the ontological seed we call zeta naught.
Which we'll get to.
Which we'll definitely get to. This isn't just a journey to understand what mathematics does or how we use it. It's really a quest to understand what it is at its deepest level. Okay, let's unpack this then. Let's start our journey way back. 6th century BCE, ancient Greece. The first explicit ontological turn in mathematics, meaning the first time philosophers really started asking, what is mathematics? In this deep way arises with Pythagoras and his, well, rather enigmatic school.
Right, the Pythagoreans.
For them, the famous maxim, one you've likely heard, was all is number. But what did that truly mean for them? It sounds almost poetic, but it was much more, wasn't it?
Oh, much more. For the Pythagoreans, this wasn't simply a metaphor or some philosophical abstraction. What's really striking is that numbers weren't just abstract symbols of quantity, a convenient way to tally sheep or count days.
Right, not just labels.
No, they were considered the very substance of reality, the fundamental building blocks from which everything else was made. Imagine a universe where the essence of every object, every phenomenon, every sound was fundamentally numerical.
The substance.
Yeah. They observed harmony in music, those precise mathematical ratios of vibrating strings producing consonant intervals. They saw elegant proportion in geometry, the fixed relationships between sides of a triangle or the segments of a circle, and they perceived the predictable, ordered movements of the cosmos.
The planets, the stars.
Exactly. For them, all of it expressed an underlying numerical resonance, a deep vibrational truth that was both cause and effect. It wasn't just described by numbers, it was numbers.
So this worldview made mathematics simultaneously a rigorous science and a profound mysticism, didn't it? It wasn't just one or the other.
Absolutely. For a Pythagorean, to truly understand numbers wasn't just about calculation or geometry. It was about unlocking the fundamental code of existence itself. It was a path to cosmic understanding, maybe even spiritual enlightenment.
You can imagine the depth of that belief. That every sound, every star, every atom, every thought just hummed with this intrinsic numerical truth that you could discover and understand.
It's an incredibly holistic and all-encompassing worldview, isn't it? The universe itself as a grand, beautiful equation.
Yeah. So that deep Pythagorean insight, that numbers are the very essence of reality, that became fertile ground for later thinkers. And building directly on that, we see Plato, one of history's most influential philosophers. He takes these ideas to an entirely new level, a transcendent level. How did he elevate the status of numbers even further?
Well, Plato's philosophy indeed built upon this foundation, but he gave mathematical entities a unique ontological home, you could say. He taught that numbers in geometrical forms didn't just exist in our physical reality, they belonged to a separate, transcendent, and eternal realm of forms.
The realm of forms, okay.
Think of it like this. The perfect circle, the ideal triangle, the infinite sequence of integers. These weren't human inventions, ideas we just conjure up in our minds.
Not just concepts.
Not just concepts. For Plato, they were perfect, immutable realities that existed independently, untouched by the imperfections and changes of our physical world. Our everyday reality, the one we perceive with our senses, merely offered imperfect approximations, shadows, reflections of these perfect forms.
So when I draw a circle on a piece of paper,
it's never truly perfect.
Right.
It's always a slightly flawed physical manifestation of the ideal eternal form of circularity that exists in this higher realm.
got it. So for Plato, mathematics wasn't just a descriptive tool then. It was the most direct bridge, like a pure intellectual path between our messy, changing sensory world and ultimate unchanging truth.
Yes, exactly. It offered a way to access something beyond our immediate, imperfect perception, almost like a spiritual discipline that purifies the mind. It suggests that our capacity for mathematical thought is a key to unlocking fundamental truths about reality that are otherwise inaccessible.
That's a huge claim for mathematics.
It is. And Plato established this transcendent view of mathematics that would profoundly shape philosophical thought for over 2 millennia. This perspective fundamentally suggested that mathematics is discovered by minds.
Discovered, not invented.
Exactly. Implying it exists objectively, out there, waiting for us to uncover it, rather than invented by us. This gave mathematical entities an incredibly high ontological status. They were positioned as more real, more perfect, and more enduring than anything in our physical world.
So mathematics essentially got its own independent, self-sufficient existence in Plato's view.
Pretty much, yes. A realm unto itself.
However, not everyone was on board with Plato's grand transcendent vision, right? His most famous student, Aristotle, for instance, he had a rather different take, more grounded maybe.
Absolutely. Aristotle, with his feet firmly planted in the empirical world, his focus on observation and classification, He deeply resisted this Platonic exaltation of numbers to some separate, perfect realm.
He wasn't buying the forms.
Not in the same way, no. He saw numbers not as independent, transcendent entities existing in some ethereal domain, but rather as abstractions drawn directly from sensible things.
Okay, abstractions from things.
Yes. When we talk about three, for example, we're not accessing some universal threeness that exists on its own. Instead, Aristotle argued, we are generalizing from our observations of three apples or three stones or three ideas.
So we see groups of three and our mind abstracts the concept.
Exactly. For him, numbers lacked their own ontological realm. They existed solely in the mind, derived from physical reality, the world we experience with our senses. Our minds observe similarities in groups of objects and then abstract the concept of number from those observations.
So this profound disagreement then between Plato and Aristotle mathematics as eternal being out there versus mathematics as mental abstraction derived from experience, this really sets the stage for millennia of philosophical wrestling, doesn't it?
It absolutely does.
This early tension feels like a foundational split.
It is. And it raises that fundamental question that echoes through the centuries and continues to challenge us. Is mathematics something out there, inherent in the cosmos, an objective blueprint awaiting discovery?
The Platonic view.
Right. Or is it something in here, a product of human thought, our minds actively constructing and generalizing from our observations of the world?
The Aristotelian view, roughly.
Roughly, yes.
Yeah.
This question of objective existence versus subjective construction really defines much of the subsequent historical inquiry into mathematical ontology.
Okay, so moving beyond the classical world now into late antiquity and the Middle Ages, how did these profound ideas about numbers and forms evolve? It seems Neoplatonism, a later development of Plato's philosophy, kept his vision going, but maybe with an even more mystical or theological spin.
That's right, yeah. Thinkers like Plotinus and Proclus, key figures in Neoplatonism, they deeply integrated Plato's ideas with a strong sense of divine emanation. They saw numbers not just as ideal forms, but as emanations of the One.
The One, like the ultimate source.
Exactly. A singular, ultimate, and utterly simple divine reality. They conceived of reality as cascading outward from this perfect unity into increasing multiplicity, with numbers serving as the first, most perfect expressions of this divine order.
Wow, so numbers are like the first step away from pure unity.
In a sense, yes. For them, mathematics was less about rigorous calculation, actually, and more about spiritual ascent, a mystical ladder, you could say, a path for the soul to purify itself and lead it back toward divine simplicity, towards the One.
So math becomes a spiritual practice.
Very much so.
Mm.
To understand the numerical order of the cosmos was, in essence, to understand the very structure of the divine mind. It was a pathway to reconnect with the ultimate source of all being. It really blurred the lines between philosophy, theology, and mathematics.
Fascinating. And then as we move further into medieval scholastic traditions, especially in the universities that were starting up, mathematics found its place in an even broader intellectual and theological framework, didn't it? Often seen as a key to understanding God's creation.
Precisely. Influential thinkers like Boethius, who was crucial in preserving classical knowledge for the Latin West early on.
Right, very important figure.
And later, Thomas Aquinas, the towering theologian of the High Middle Ages, they placed arithmetic and geometry right at the heart of the quadrivium.
The quadrivium, remind us.
It was the higher division of the 7 liberal arts. It encompassed arithmetic, geometry, astronomy, and music, all disciplines fundamentally rooted in number and proportion.
Got it. The mathematical arts.
Essentially, yes. For them, mathematics became an indispensable way of reading the book of nature itself. It was seen as deciphering God's design written in numbers and ratios, understanding the inherent mathematical harmony embedded in creation.
So studying math was like studying God's blueprint.
That was the idea. It was believed that through mathematics one could glimpse the Creator's plan, making the study of numbers and forms not just an intellectual pursuit, but a form of devotion, an insight into divine intelligence and order. It was a bridge between the empirical world and the divine.
Okay. Then the Renaissance hits this period of immense cultural and scientific rebirth. It brought a fascinating shift, didn't it? While still revering classical knowledge, mathematics seemed to take on a new, almost commanding role, not just describing the universe, but actively revealing its underlying structure.
It truly did. During the Renaissance, there was this fervent belief that mathematics was the hidden architecture of nature, the secret code just waiting to be deciphered.
The hidden architecture, I like that.
Yeah. You see this wonderfully exemplified in the work of Johannes Kepler, the astronomer. and his passionate, almost obsessive search for cosmic harmony and the laws governing planetary motion.
His laws of planetary motion, yeah.
Right. He didn't just describe how the planets moved. He believed the planets moved in elliptical orbits, following precise mathematical laws, not simply because physical observation or nascent physics dictated it, but because geometry itself demanded it.
Geometry demanded it.
Yes. He sought the archetypal reasons, the ideal mathematical forms and proportions that compelled the planets to move as they did. The ancient idea of the music of the spheres, it wasn't just a metaphor for Kepler.
He took it literally.
For him, it was literal ontology. Mathematics, in this view, dictated physical law. It imposed its perfect order on the cosmos, revealing the divine architect's grand design through numbers.
So here, mathematics was seen less as a human invention and more as the divine grammar of reality. It wasn't something separate describing reality. It was the inherent language that reality spoke.
Exactly, a language that could be learned and understood by humans.
You can really feel the grandeur in that perspective, can't you? A profound sense of awe at the universe's inherent beautiful order revealed through mathematical principles.
This is a critical point. What's truly insightful here is how scientific observation became inextricably intertwined with a profound belief in an underlying inherent mathematical order, often seen as divine in origin.
So it wasn't just a tool anymore.
Not just a descriptive tool for measuring what was observed. It was seen as the very reason why things were the way they were. It suggests a deeper causative, almost constitutive role for mathematics in the universe's fundamental being. It wasn't just a convenient lens. It was the bedrock.
Okay, moving into the 17th century, the rise of modern science and philosophy, this is a new era. Mathematics becomes, maybe paradoxically, both more abstract in its formal systems, but also more intimately grounded in our understanding of the universe and even the nature of human reason itself. René Descartes, for example. He saw mathematics as absolutely foundational to his entire philosophy, his quest for certainty.
He absolutely did. Descartes, famously embarking on that quest to doubt everything he possibly could.
I think, therefore I am.
Exactly. He sought an absolute, unshakable certainty upon which to build all knowledge. And he found this grounding in what he called clear and distinct ideas.
Clear and distinct.
And mathematics, particularly geometry and algebra, served as the supreme paradigm for such ideas. For him, these disciplines weren't just tools you applied to solve problems. They were woven into the fabric of reason itself.
Wow, into reason itself.
Yes. The clarity, the rigor, the undeniable self-evident conclusions of mathematical thought became the ultimate standard, the very model for all true, indubitable knowledge. He believed that if we could reason in philosophy with the same clarity and deductive power as in mathematics, we could achieve universal certainty.
So math was the gold standard for thinking.
It wasn't just a way of thinking, it was the way of thinking for genuine knowledge in his view.
And Gottfried Leibniz, a true polymath, contributing everywhere, philosophy, math, logic. He also had a similarly profound and, expansive view of mathematics, didn't he? Even envisioning a kind of universal language.
Indeed. Leibniz didn't just contribute to the independent discovery of calculus.
Right, the famous Newton-Leibniz controversy.
Exactly. He envisioned a much grander universal calculus, or characteristica universalis, a symbolic language system that he believed could reflect nothing less than the divine order of creation.
A universal language reflecting divine order. That's ambitious.
Hugely ambitious. And his famous discovery and development of binary numbers, that system of zeros and ones we all use constantly now.
The basis of computing.
Right. For Leibniz, it wasn't merely a mathematical trick or a convenient notation for computation. He considered it an ontological revelation.
Ontological? How so?
He actually speculated that the universe itself might be reducible to the play of 0 and 1, absence and presence, void and being. He saw binary as a fundamental, elegant, and inherent code for reality, long before anyone dreamed of electronic computers.
That's incredible.
He was convinced that in this binary system lay the simplest expression of God's creative power, where everything sprang from nothing, 0, and God, 1.
That's amazing. Leibniz's idea of binary numbers feels not just modern, but almost prescient, anticipating so much of our digital age. Yet, he saw it as something far deeper than just computation.
Much deeper. He saw it as a profound, fundamental truth about existence itself. For him, the binary system wasn't just a useful human convention. It reflected a deep, elegant, inherent structure of the cosmos itself. a divine logic made manifest in the simplest numerical forms. It was the very language through which existence expressed itself.
Wow. And then, of course, Isaac Newton. We usually think of him for his revolutionary laws of physics.
Gravity, motion, optics.
Exactly. But while his work reshaped our understanding of the physical world, his view of mathematics was also deeply ontological, wasn't it? Rooted in his theological understanding of the universe.
Precisely. Newton, despite his towering scientific achievements, was a deeply religious man, and he saw mathematics as fundamentally embedded in God's absolute space and time.
Embedded in space and time themselves.
Yes. His groundbreaking invention of calculus wasn't just a powerful tool for describing physics, motion, and gravity. It was, for him, a language that expressed how God ordered creation. It was the means by which the divine design of the universe was made manifest and intelligible to human reason.
So, for these early modern thinkers, Descartes, Leibniz, Newton mathematics was far more than just practical.
Much more. It was ontological structure, mirroring the order of existence, directly reflecting the divine blueprint of the cosmos. Their work really cemented the idea that the universe was like a giant clockwork mechanism.
Right, the clockwork universe idea.
And mathematics was the language of its gears, both designed by God and inherently part of its being.
Okay, so connecting this to the bigger picture,
Yeah.
these figures really cemented that powerful idea that mathematics wasn't just a way to describe the universe, like an external tool we apply.
Right. Not just a manual for it.
Instead, it was intrinsically part of its fundamental being, its very essence and structure, often with that profound connection to a divine architect who designed it all mathematically.
It was seen as the universe's internal operating system, perhaps.
But then, as we move into the 18th and 19th centuries, philosophy takes this fascinating and really profoundly influential turn inward. It shifts its focus towards the structures of the human mind, rather than outward towards the divine blueprint or external forms. Immanuel Kant, for instance. He fundamentally changed how we thought about mathematics, didn't he? Placing human consciousness right at the center.
He absolutely did. It's often called the Copernican revolution in philosophy for a reason. Kant argued that numbers and geometry are not external realities we passively discover out there in the world, like finding a new continent.
Not discovered.
No. Instead, they are a priori forms of intuition, meaning they arise directly and necessarily from the very structure of the human mind itself.
A priori, meaning before experience.
Exactly. Think of these as the fundamental built-in operating system or pre-installed software of your mind. For Kant, space and time themselves aren't objective, external entities we perceive directly.
Not things out there.
No, rather, they are mental frameworks through which all experience is filtered. Our minds don't just receive raw data. They actively organize it spatially and temporally.
Ah, okay. The mind imposes structure.
Precisely. And this, he claimed, is why mathematics is universal and necessarily true for us, not because it exists independently in some Platonic realm, but because every human mind universally imposes these same inherent structures on everything it experiences. We can't help but perceive the world through these mathematical lenses.
Okay, let's unpack this a bit more because this is a truly revolutionary idea. If I'm getting this right, Kant is essentially saying mathematics is like a pair of special, inescapable glasses we automatically wear.
That's a great analogy.
To see and organize the world, it's a lens we put on reality, rather than something out there waiting to be found without our mental intervention.
Yes, it's a way our minds organize reality, making it intelligible rather than a feature of reality itself, independent of us.
So it explains universality through shared mental structure.
Exactly. Our minds aren't just receiving information. They're actively shaping it and structuring it. Yeah. And mathematics, particularly geometry and arithmetic, is a fundamental aspect of that inherent shaping mechanism. It explains why mathematical truths feel necessary and universal to us, because they're derived from the very conditions of our knowing. We literally cannot conceive of a world without space and time, and thus without the mathematics that flows from those intuitions.
Wow, okay. And then Wilhelm Friedrich Hegel, another giant of German philosophy, he takes this idea of mathematics being rooted in consciousness even further, doesn't he? Seeing it as part of a larger historical dynamic process.
Indeed, Hegel interpreted numbers and mathematical concepts not as static eternal truths fixed for all time.
Not like Plato's forms.
No, but as moments of the dialectic. This is a key Hegelian concept, that dynamic process where an initial idea, a thesis, inevitably encounters its opposite, an antithesis, and from the tension between them, a new, richer idea, a synthesis, emerges.
Okay, the dialectic. The thesis, antithesis, synthesis.
Right. For Hegel, mathematics wasn't some unchanging realm. It was historical. profoundly bound up in the unfolding of thought itself, meaning it evolves and develops as human consciousness and understanding evolve through this dialectical process.
So math itself changes over time.
Its understanding certainly does. Concepts like infinity or zero weren't always understood the same way. Their meaning deepens and transforms as human thought, as spirit, in Hegel's terms, progresses through history. It's a deeply dynamic and interconnected view where mathematical ideas are part of a continuous process of intellectual and spiritual development, reflecting the very journey of human reason.
This period truly marks a crucial shift then, doesn't it? Mathematics begins to lose its divine grounding, its connection to a cosmic blueprint or a transcendent realm.
It becomes more secularized in a way.
And becomes distinctly anthropological, rooted squarely in the inherent structures and the historical unfolding of human thought and consciousness.
It's a profound move from the cosmos to the cognitive, from an external given to an internal construction.
Yeah. But this is a pivotal point, isn't it? It raises that important question that still challenges us today. If mathematics is primarily in our heads, or a product of human consciousness and its structures, how do we then fully explain its uncanny, consistent, undeniable effectiveness in describing the external physical world?
Right, the unreasonable effectiveness, as Wigner called it.
Exactly. Why does it work so perfectly from subatomic particles to galaxies if it's just a mental construct? That's the big puzzle Kant leaves us with, perhaps.
It's a huge puzzle. How does the structure of our minds seem to map so perfectly onto the structure of the universe? That remains a profound question.
So the 19th century, it really pushed mathematics to a kind of breaking point, didn't it? Introduced a profound unease, even a crisis, especially around one concept, infinity, which seems so abstract, yet it caused such foundational upheaval.
It was a truly seismic shift, yeah. It fundamentally altered how mathematicians thought about numbers. On one side, you had a titan like Carl Friedrich Gauss.
The prince of mathematicians.
Yeah, right. He was extremely wary of infinity. He famously insisted it should never be treated as an actual completed entity in mathematics. He saw it as useful for limits, like a process approaching something endlessly, but not as something that could be fully grasped or manipulated as a concrete finished number.
He thought it was dangerous territory.
He feared it would introduce paradoxes and inconsistencies, yeah. Keep it potential, not actual.
But then came Georg Cantor, a revolutionary figure. He basically walked right into that dangerous territory, didn't he?
He absolutely did. He dared to tread where others feared. Cantor boldly introduced the theory of transfinite numbers, which directly challenged Gauss's caution. He didn't shy away from infinity. He embraced it. He proved, through rigorous mathematical argument, that infinities actually come in different magnitudes.
Different sizes of infinity.
Exactly. A truly mind-bending idea at the time, and one that initially met with fierce opposition, even ridicule.
And this is where it gets really fascinating for anyone who just thinks infinity is just infinity. Cantor didn't just speculate. He showed there's not just one infinity, but a whole hierarchy.
LF naught, LF1.
Right. He demonstrated, for example, that the infinity of all positive whole numbers, 1, 2, 3, which he called Aleph dollars, Aleph naught, is actually smaller than the infinity of all real numbers, like all the points on a line segment.
That continuum.
Yeah. Imagine trying to count all the positive whole numbers. You could theoretically do it, given infinite time. But if you try to count all the points on a line, even a tiny segment between 0 and 1.
You can't put them in a one-to-one correspondence. There are just more of them.
Exactly. You'd never exhaust them. For Cantor, infinity was as real as any finite number, a tangible, if immense, quantity capable of being quantified and categorized.
He even went further, didn't he? Relating it to the divine.
He did. He spoke of the absolute infinite, which he equated with God himself. He saw his work almost as a divine revelation, not just a human invention.
But this radical departure, this audacious redefinition of infinity, it was met with fierce resistance from many in the mathematical community.
Oh, absolutely. Leopold Kronecker, another prominent mathematician, Cantor's former teacher even.
Right, their relationship became quite strained.
Yeah. Kronecker famously declared, "God made the amateurs, all else is the work of man."
Wow, that's a strong statement.
It is. It was a powerful return to mathematical minimalism, maybe intuitionism, arguing that only the whole numbers, the simple counting numbers that are intuitively graspable, had true ontological legitimacy, the direct grounding in reality or divine creation.
So he saw Cantor's work as what? Dangerous.
Dangerous abstraction, yeah.
Hmm.
Divorced from anything truly real, he called it a disease from which mathematics would eventually recover, leading down a perilous, paradoxical path. The battle lines were definitely drawn.
So in the face of this profound crisis, with the very concept of number being questioned and expanded in such radical and, well, terrifying ways for some, mathematicians felt this urgent need to shore up the foundations, didn't they? To find certainty again.
Exactly. They needed bedrock. Figures like Richard Dedekind, who developed Dedekind cuts to formally define real numbers.
Building them from the rationals, yeah.
And David Hilbert, who launched his ambitious Hilbert's program, they recognized the looming instability. They sought to secure mathematics with rigorous axioms and set theory.
The formalist approach.
Right. The idea was that mathematics could be built on a small set of self-evident truths, axioms, and a rigorous theory of sets. Their ambition was to treat mathematics as a purely logical edifice.
Built step by step, purely deductively.
Exactly. Built from fundamental, consistently defined rules and logical deductions, free from intuition, paradoxes, or appeals to questionable concepts like actual infinity. They hope to create an unshakable, perfectly consistent, and complete mathematical system.
The dream of a perfect system.
But despite these valiant efforts to build this perfect, logical, self-contained structure, the cracks were still visible, aren't they? Simmering beneath the surface. Infinity had destabilized the very foundations of number, exposing fundamental questions about its nature.
And with it, the ontological security of mathematics. The certainty of what numbers were and how they truly existed was deeply shaken.
Yeah, that dream of a perfectly consistent and complete system was about to face its greatest challenge.
This brings us to a crucial point about mathematical truth itself. What's truly profound here is how a seemingly abstract concept like infinity, something we rarely encounter directly, could create such a profound foundational crisis within mathematics.
It really shook the core.
It challenged the very definition of what mathematics is, forcing a reevaluation of its fundamental nature, its existence, and the limits of human reason to fully grasp it. It was a crisis that would really redefine the 20th century.
Okay, so the 20th century opens with this immense optimism within the mathematical community. Davy Hilbert's program especially was this beacon of hope.
Hilbert's famous 23 problems, yeah.
Mm-hmm.
A roadmap for the future.
Right. He aimed to prove that mathematics could be made completely consistent, entirely certain, and universally provable through a finite set of formal axioms. It was this grand vision of mathematical perfection, where every true statement could eventually be demonstrated within the system, banish all doubt, all paradox.
A beautiful dream, really. A self-contained universe of perfect logic.
But that dream, well, it shattered decisively and famously in 1931 with the publication of Kurt Gödel's incompleteness theorems.
Yeah, Gödel. He delivered a conceptual hammer blow to this optimistic vision.
A hammer blow is right. Gödel showed, quite astonishingly, that any sufficiently rich formal system, and by that he meant any mathematical system complex enough to contain basic arithmetic.
So most of mathematics we use.
Right. Any such system is either inconsistent or incomplete.
Inconsistent or incomplete. Let's unpack that.
Okay, so inconsistent means it contains contradictions, which is obviously bad, but incomplete. That's the really mind-bending part. It means there will always be true statements that cannot be proved within the system itself.
True statements that the system itself can't reach through its own rules.
Exactly. You can't capture all truth from within, no matter how carefully you construct your axioms.
So what does this all mean for you, for someone trying to understand the nature of truth itself, not just in math, but maybe beyond? This isn't just some technical puzzle for logicians, is it?
Not at all. It's a philosophical earthquake. It implies there are inherent fundamental limits to what we can ever formally prove, even in a system as rigorous and seemingly perfect as mathematics. It introduces a kind of irreducible mystery at the heart of logic itself.
The implications were absolutely profound, and they still resonate today. It meant mathematics could never fully justify itself from within its own axiomatic system. It couldn't prove its own consistency without using methods from outside, from a potentially even larger, possibly unprovable system.
You can't pull yourself up by your own bootstraps, logically speaking.
Exactly. If mathematics were only a formal game of symbols, just a self-contained logical structure, then its truths would forever exceed its own rules. There would always be true statements, Gödel sentences, whose truth we could intuitively grasp, perhaps, but which we couldn't formally prove within that given system.
So if the truths exist beyond the proofs,
Then it forced ontology, that fundamental question of being, to return with immense force. If mathematical truths exist beyond our formal proofs, then mathematics must have a deeper grounding outside mere syntax, outside the formal symbols and rules themselves, if its truths are to hold any meaningful status.
Its truth must reside somewhere else.
Right. It couldn't simply be a self-contained game. There had to be something more that made those unprovable statements true.
So connecting this back to our deep dive, Gödel's work makes us confront these inherent limits of purely formal systems. It powerfully brings the question of mathematical being, what mathematics truly is, and where its truth ultimately resides right back to the forefront with renewed urgency.
After centuries of trying to formalize it away into a self-sufficient logical structure.
Right. Gödel basically says, nope, there's something outside the system. It tells us there's something more to mathematical reality than just axioms and rules. Okay, so after Gödel dropped this bombshell, revealing these inherent limitations, you might think everyone would converge on a new understanding, but that didn't happen, did it?
Not really, no. The philosophical positions on mathematics didn't coalesce. Instead, they diverged dramatically. It led to a really vibrant, but still fragmented philosophical landscape that continues to this day. There's still no single universally accepted answer to what is mathematics.
So what were some of the main camps that emerged or solidified after Gödel?
Well, you had the Platonists, figures like Gödel himself, actually. He interpreted his incompleteness theorems not as a defeat for mathematics, but as powerful evidence for Platonism.
Oh, so.
He argued that those unprovable truths simply pointed to a reality beyond our formal systems, a transcendent realm of mathematical forms awaiting our discovery, echoing those ancient Greek ideas. Gödel believed human intuition could grasp these truths because the mind was somehow connected to this objective Platonic realm. The unprovable truths were true because they accurately described this independent mathematical reality.
Okay, so Gödel becomes a Platonist. What else?
Then there were the formalists, the intellectual heirs to Hilbert. Despite Gödel's findings, they largely doubled down, in a sense, and reduced mathematics primarily to symbolic manipulation.
Even after Gödel showed the limits of formal systems.
Yeah. For them, the purpose of mathematics was still to create consistent and elegant formal systems. They argued that its beauty and utility lay in the consistency and coherence of its internal rules, even if completeness, the ability to prove all truths, was demonstrably impossible. Mathematics was essentially a self-consistent game played with symbols, incredibly useful for modeling the world, but not necessarily revealing some deeper inherent truth about an independent reality.
So, Platonists say math describes a real separate realm. Formalists say it's more about the consistent game itself. Any other major views?
Oh, yes. You also had constructivists, like the influential Dutch mathematician L.E.J. Brouwer. They took a very different path. They insisted that numbers and mathematical objects exist only as mental constructions.
Only if we can build them in our minds.
Essentially, yes.
Okay.
For them, a mathematical entity only truly existed if it could be explicitly constructed or found by a human mind in a finite number of steps. This was a very human-centric, you might even say restrictive view. It rejected proofs that didn't involve explicit construction, like proofs by contradiction for existence, which significantly narrowed the scope of what they considered acceptable mathematics.
Interesting. So a much more mind-dependent view.
Very much so. Then there were phenomenologists, like Edmund Husserl. He argued that mathematics arises from consciousness itself, focusing on the lived experience and intuition of mathematical ideas. For Husserl, mathematical objects aren't empirical things in the world, nor are they purely psychological states. They are ideal objects that are grasped through intentional acts of consciousness. It's about the structure of experience itself.
Okay, arising from consciousness. And finally,
you have structuralists and category theorists, figures like William Lovere. They claim that mathematics is fundamentally about relations and structures, not objects themselves.
structures, not things.
Exactly. For them, what matters isn't what individual numbers are in isolation, but how they relate to each other within larger abstract systems and structures. They argue that mathematical objects are defined by their place in a structure, not by their intrinsic nature.
Can you give an example?
Sure. Like, the number 2 isn't some singular thing you can point to. It's defined by its position within the structure of natural numbers. It comes after 1, before 3. It's the result of 1 plus 1. It's a factor of 4, and so on. Its identity comes from its web of relationships within that mathematical structure.
Got it. So it's all about the patterns and connections.
Pretty much.
It certainly sounds like everyone has a piece of the puzzle, doesn't it? Each view offers a genuinely profound insight into some aspect of mathematics, but maybe no one has the whole picture.
That seems to be the case.
Despite their undeniable insights and the power of their individual frameworks, you're kind of left with this lingering, unresolved paradox. A feeling of incompleteness in our understanding of what mathematics truly is. It's almost as if each theory grasps one facet of this incredibly complex gem, but struggles to describe the whole thing.
That's precisely it. And our source material highlights this beautifully in its summary of this period. None resolve the paradox. Mathematics is too universal to be human invention, too generative to be mere abstraction, too dynamic to be eternal stasis.
Universal but not just invention. Generative but not just abstraction. Dynamic but not just static. Yeah, those are the tensions.
Right. And this raises that important, persistent question that brings us right to the present moment. How can something feel so universally true, so undeniably effective in describing our world, so deeply intuitive sometimes, yet be so incredibly hard to pin down in its fundamental nature, its very being?
How can it be all these things at once? Universal yet dynamic, abstract yet concrete, discovered yet seemingly constructed.
That is the fundamental ontological riddle that history leaves us with.
Okay, so after this incredible historical journey from ancient Greek mystics believing in numerical essences all the way to modern logical paradoxes shattering our certainties, where do we stand? What's the central, persistent problem we're still trying to solve about the true nature, the ontology of mathematics?
Well, the unresolved riddle is remarkably clear, I think. It's distilled into those three persistent paradoxes that no single historical view has fully managed to reconcile.
Let's recap them quickly.
Okay. First, if mathematics is only symbols, just a formal game, it floats unanchored. It lacks any deep connection to reality or ultimate truth. It risks becoming arbitrary. How can something so powerful be just human-made rules?
Right, the effectiveness problem.
Second, if it's eternal, existing in some fixed Platonic realm, it risks being detached from the living process of reality. It struggles to account for its dynamic nature, its evolution, its generativity, and its intimate connection to scientific discovery. How can something static connect so well to a dynamic universe?
The detachment problem.
And third, if it's subjective, purely a product of the human mind, it cannot explain its uncanny universality and consistent effectiveness in the external world. Why does our mental structure match the universe so well?
The universality problem.
Exactly. Those are the three fundamental contradictions that previous philosophies have grappled with. Each finds a partial answer, maybe, but leaves the overall mystery intact.
Okay, so this sounds like we need a completely new way of thinking about mathematics' origin point, doesn't it? A different kind of starting place, maybe an ontological generator that can somehow resolve these profound contradictions.
That's the argument. We need something that doesn't just describe the problem, but offers a path forward.
A new foundation.
Exactly. What seems needed is a new ontological generator, a foundational principle where mathematics emerges not from arbitrary human axioms, not solely from human thought and its structures, and not from a distant, unchanging Platonic realm, but rather from the coherence of reality itself.
From the coherence of reality itself, what does that mean?
It means finding a source, a generative principle, where mathematics isn't just observed or invented, but fundamentally generated as an intrinsic, emergent aspect of existence. This tries to resolve that dilemma of discovery versus invention by suggesting mathematics is an inherent, unfolding property of reality.
Okay. And this is where the proposed concept of zeta naught comes in, offering a fresh perspective that tries to unify these disparate historical insights.
Yes, that's precisely where the author of our source material directs us. They propose zeta naught as the ontological seed, a conceptual framework aiming to be that new generative foundation.
Zeta naught, an ontological seed.
Right. It's described as encompassing three key interconnected concepts: the coherence vacuum, the seed equations, and the eigenvalues that define mathematics as an emergent ontology.
Okay, coherence vacuum, seed equations, eigenvalues. Let's break that down a bit. What's the coherence vacuum? Sounds empty.
Well, it isn't an empty void in the usual sense. It's described more like a field of pure potential, a kind of pre-mathematical substratum where order is not yet manifest, but is poised to emerge. Think of it as the ultimate raw material of existence, inherently seeking coherence and pattern.
So, potential seeking order.
Exactly. It's the ground state from which complexity arises, a fertile nothingness, if you like, that yearns for mathematical form. This tries to address that floating, unanchored paradox because it ties mathematics directly to the very potential of being.
Okay, so it's grounded in potential reality. What about the seed equations?
From this coherence vacuum, the idea goes, arise the seed equations. Now, these aren't equations we necessarily write down on a blackboard. They're thought of as fundamental self-generating principles, or maybe meta laws, that govern the emergence of structure from that
What
potential.
rules of emergence?
Kind of, yeah.
Yeah.
The initial rules, not invented by us, but inherent in the coherence vacuum, that dictate how reality will organize itself mathematically. They are like the prime directives, the foundational algorithms for reality's mathematical unfolding. They're seen as dynamic and generative.
Which addresses the static Platonism issue.
Right. It addresses the paradox of mathematics being both eternal in principle and detached, because here the eternity is in the principle of generation, not in fixed static form.
Okay. Coherence vacuum, seed equations, and eigenvalues. That's a term from linear algebra.
It is. And here it's used analogously. The eigenvalues in this context refer to the stable characteristic states or inherent mathematical properties that define reality's emergent structures. In math, an eigenvalue represents a kind of stable value under transformation.
Right.
Here, they represent the stable, intrinsic numerical values that reality prefers or settles into as it organizes itself according to the seed equations within the coherence vacuum.
Like fundamental constants or symmetries.
Exactly. They could be things like fundamental constants, symmetries, the specific patterns we observe. These eigenvalues are not subjective. They emerge objectively from this generative process. And that addresses the paradox of universality, why math works everywhere without making it purely a human construct. It emerges from reality's self-organization.
So after this incredible historical journey exploring 2 millennia of philosophical struggle, we're finally looking at a concept, zeta naught, that tries to bridge all these gaps. The universality, the generativity, the dynamic nature, the objective existence, providing a truly generative principle for mathematics, one that's intrinsic to reality itself.
That's the ambition, yes. It's a monumental undertaking, really, moving beyond the historical, either dichotomies discovered or invented, static or subjective, towards an emergent, integrated understanding.
That's fascinating.
It is. What's really compelling here is the attempt to find a principle that reconciles the universality of mathematics with its dynamic, evolving nature and its deep connection to reality. By placing its emergence squarely within the fabric of reality itself through this interconnected concept of zeta naught, rather than outside in a transcendent realm or merely inside the human mind, well, it offers a potential path toward a unified understanding of what mathematics is.
Resolving those long-standing paradoxes by proposing this inherent generative origin.
Suggesting that mathematical reality is continually unfolding, generated from the coherence of being itself. #outro.
Wow, what an extraordinary intellectual journey we've traced today. We've traveled from Pythagoras believing all is number as the very substance of reality,
The mystical beginning.
through Plato's transcendent realm of eternal forms,
Yeah.
then to Aristotle's more empirical view of mathematical abstraction. We saw mathematics evolve into the divine grammar of the Middle Ages, shaping the cosmic architecture of the Renaissance.
Kepler's geometric demands.
Right. Before the Enlightenment brought us Descartes' quest for certainty, Leibniz's universal calculus, Newton's divine spacetime, then that huge anthropological turn with Kant's mind-centric view.
Putting the mind at the center.
The crisis of infinity with Cantor's hierarchies and Kroneker's fierce resistance. And finally, Gödel shattering those dreams of perfect certainty with his incompleteness theorems.
It's quite a story. Through it all, that central, persistent question has remained. What is the true being of mathematics? Is it something we simply discover, waiting out there?
Like Plato thought.
Is it something we invent, a purely human creation?
Like maybe the constructivists lean towards?
Or is it something that inherently constitutes reality itself, its fundamental language and generative principle?
Perhaps where zeta naught is pointing.
Each epoch, each great thinker, has offered profound insights, yet ultimately left us with these lingering paradoxes about its true nature. It's really a testament to the depth of this fundamental question.
The very fact that mathematics is both so universally effective in describing our world from the quantum to the cosmic, and yet remains so deeply mysterious in its fundamental origin and ontological status, well, it tells us there's still so much more to uncover, doesn't it?
Absolutely. The journey of understanding isn't over. We're perhaps only just beginning to truly grasp its deepest roots.
And this is where the concept of zeta naught offers, well, a compelling new direction, a potential new synthesis that attempts to bridge those historical divides.
It suggests that mathematics isn't merely a language about reality, just a tool we use to describe it. Instead, it proposes that mathematics is a fundamental expression that emerges from the inherent coherence and generative principles of reality itself.
Emerging from reality.
Yes. It's an invitation, really, to consider a living, dynamic ontology of mathematics where its truths aren't static, but are woven into the very process of existence and its continuous unfolding.
So here's a final thought for you, our listeners. Next time you look at a number or a geometric shape or even a simple equation, take a moment to consider. Are you observing an eternal truth handed down from some perfect realm?
The Platonic view.
Are you seeing an ingenious invention of the human mind?
The Kantian or constructivist view.
Or perhaps, are you witnessing something far more profound, the very hum of the universe itself, emerging into coherence and form around you, maybe a manifestation of this zeta naught principle?
Food for thought.
Definitely. We hope this deep dive has given you a whole new perspective on something so fundamental, yet so often taken for granted in our daily lives. Thank you for joining us on this exploration of mathematical ontology.